Hi, my name is Nishcharati and this is my lab report for Physics 2 Lab 4. In this lab, we will predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of current and potential difference, and examine the behavior of ohmic resistors and capacitors. In this lab, the system is the circuit and the surroundings are everything else. The findings of this lab are that the circuits containing resistors in series show smaller current flow than those with parallel. The loop rule and node rule hold as per voltmeter and ammeter readings, and capacitors charge and discharge in 5 tau periods where tau is the resistance times the capacitance. We are going to be using the following physical principles. Loop rule, which states that the sum of voltages in a closed loop is zero. Ohm's law, which states that the voltage is equal to current times the resistance. And node rule, which states that the current into a node is equal to the current outside a node. The assumptions in this lab are that the wire and ammeter have zero resistance, the battery has zero internal resistance, and ideal voltmeters have infinite resistance. We construct a simple circuit using two 1.5 volt batteries, two resistors, one of which was 102 ohms and one of which was 88 ohms, and two ammeters. We connect the ammeters in series in the lab as shown from the picture in the left. Using the node rule and Ohm's law, we predict that I1 should equal I2 should equal 15.6 milliamperes. Noting the values from the lab on the left, we find that I1 is 15.4 milliamperes where I2 is 15.2 milliamperes. These values are slightly different from each other and also lower than the predicted value. This can be attributed to experimental errors due to using different ammeters and also not accounting for possible resistance in other parts of the circuit like wires, ammeters, and the battery. Now, if we replace one of the ammeters with a voltmeter, because the voltmeter has infinite resistance, it effectively creates an open circuit. As we can see from the readings from the lab, the voltmeter reads 3 volts, whereas the ammeter reads 0 amps. Due to the open circuit, there is no current, and hence there is no voltage drop. So the voltmeter should read 3 volts, whereas the ammeter should read 0 amps, as is the case from the image in the lab. Now, we now measure the voltage drop across various parts of the circuit using the voltmeter, and the expected loop voltage is 0 volts. The battery, wires, and the two resistors roughly follow and are very close to the voltage drop you would expect from them. Crucially, we expect the ammeter to have a 0 voltage drop, but it has a voltage drop of 1.1 volt. Also, the expected loop voltage is supposed to be 0 volts, but the actual measurements show a loop voltage of 0.1 volts. This can again be attributed to experimental errors due to the voltmeter. Finally, a voltmeter doesn't change the current readings because a voltmeter has infinite resistance, and when connecting the voltmeter across two nodes, there is zero current that flows through the voltmeter and it hence draws no extra current. If we put an ammeter in parallel with the 102 ohm resistor, the 102 ohm resistor effectively isn't part of the circuit anymore. As a result, the resistor we include in our current calculations is only the 88 ohm resistors. We find the current to be 0.034 amperes, but we actually observe 32.3 milliamperes, which is very similar to the predicted current. And this difference in currents can also be attributed to the resistance due to the ammeter, as we saw in the previous slide. Using the potential difference in current observations, we now calculate the resistance and find that each of the resistances is very close to the known value of these resistances. Crucially, the resistance of the ammeter is not 0 ohms, but is actually 6.5 ohms. Now we set up a circuit with the same 3 volt battery, a capacitor, and a light bulb, and measure the time it takes for the capacitor to charge after connecting the battery, and after disconnecting the battery, measure the time it takes for the capacitor to discharge through the bulb. As we can see in this image from the lab, the bulb is glowing. When we connect the battery, the light bulb is initially bright but slowly dims. The same happens when we disconnect the battery after charging the capacitor. This drop in current in each loop ends after around 82 seconds. With twice the resistance, it would take twice the time. The measured values is that the RC is equal to 16.03. This is very close to the expected value of RC, which is 17.6. Thus, to conclude, both the node rule and the loop rule are correct and valid because everything that we measured within this lab is within the experimental error. To top that off, the time constant for an RC circuit is tau is equal to RC, and it takes 5 tau for a circuit to almost completely charge or discharge. There is errors in this experiment like instrumentation error in the ammeter and voltmeter as noted before, and there could also be human error in measuring the time for the RC circuit. If we were doing this lab online and we used an ideal ammeter, because the ideal ammeter would have zero resistance, the measured current reading would actually be higher. And if we were doing this lab online and we used an ideal battery, you would expect the ideal model to take a few nanoseconds for the capacitor to charge. In our real circuit, this would take longer due to internal battery resistances. Thank you.